successor to the Hubble telescope, just about ready now to produce images of the universe like we have never seen before.
It's also one of the most complicated pieces of technology ever built. It contains over 3,000 sensors that continuously monitor the status of the hardware, so that technicians on the ground can keep an eye on what's happening.
The James Webb Telescope has fundamentally altered our understanding of the cosmos. Often described as a cosmic time machine, James Webb has unlocked mysteries of the universe by peering into deep space, revealing galaxies and phenomena from the very dawn of time. But alongside these discoveries, the premier observatory has presented findings that challenge and even break parts of established cosmological theories, shaking the foundations of our understanding of the universe's formation and evolution. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. First, we have to remember exactly what James Webb is, because as remarkable as it isn't capable of answering all of our cosmic questions even with its newfound power. Sure, James Webb is a large, cold observatory with high-resolution capabilities that's optimized to observe the universe at long wavelengths, from 1.6 to 28 microns, and it can perform imaging in dozens of different wavelength ranges, as well as spectroscopy on individual objects. However, the telescope also has several important limitations. For instance, it has a narrow field of view, so it can't observe very much of the universe at once. It's incredibly oversubscribed, with about 10 high-quality proposals for observing rejected for everyone that's accepted. It takes much longer to perform spectroscopy on an object than it does to conduct imaging, severely limiting how many objects can be spectroscopically analyzed. And it can't image objects in multiple filters simultaneously. The greater the number of sets of wavelengths you want to perform photometric imaging at, the longer you need to observe with James Webb. But even with these restrictions and limitations, there's a tremendous amount of novel science that James Webb is uniquely equipped to conduct. In particular, the telescope was expected to break cosmic records such as the most distant or earliest example of certain classes of objects, as it was designed with those goals in mind. However, there were a whole suite of new discoveries that were both unexpected and suddenly possible thanks to Webb's capabilities. And those are among the most exciting aspects of science with James Webb, or any new observatory for that matter. There's a phrase that astronomers and physicists use all the time that's virtually unheard of by people outside of those fields: discovery potential. There were two sets of reasons astronomers were so excited about James Webb era when it came to science. The first was what you'd expect. With all of these novel capabilities enabled by new technologies, a large primary mirror in space, owing to its segmented and folding nature, extremely cold temperatures owing to a 5-layer sun shield, pristine optics and instruments owing to advances in instrumentation and clean room technology, and so on. There are a number of records that, just from its designed capabilities, James Webb was certain to shatter. These were the slam-dunk justifications for the Webb. But the second set of reasons is profound, not just for the observatory, but in so much of physics and astronomy in general. Whenever you build an instrument, observatory, or machine that surpasses all previous limits of all similar endeavors, particularly over the specific range of parameters that similar endeavors were sensitive to in the past, and where you then use that instrument, observatory, or machine to look in new locations, or even to look at objects or phenomena that you've looked at previously. Those new capabilities enable something that simply isn't possible without them: the possibility of discovering something new simply by looking with this new tool. All previous endeavors wouldn't be sensitive to such a new discovery, but simply by probing the universe with this new tool, the possibility of finding something surprising, or even revolutionary, is suddenly within reach. It should come as no surprise, then, to learn that James Webb has brought us many new discoveries that fall into both categories. Yes, we've set many new cosmic records with the telescope, exactly as we would have expected. With longer wavelength and higher resolution capabilities than Hubble, Spitzer, Sophia, or any of the world-class ground-based optical and infrared observatories in our arsenal, ultra-distant stars, quasars, and galaxies were exactly the types of objects that James Webb was designed to detect. There are many examples of cosmic distance records that have been broken and revised since the James Webb era began in 2022, and they're just as impressive as you might have imagined. Many have called James Webb a cosmic time machine for its ability to see back farther into our cosmic past than any other optical or infrared observatory in history. Yes, we can see the Big Bang's leftover glow with microwave light, and we can potentially see the signature of neutral hydrogen atoms even before the formation of stars with far infrared and radio astronomy, thanks to the 21 cm spin-flip transition of hydrogen. Its ability to observe longer wavelengths than ever before at such high precision, plus its ability to conduct spectroscopic follow-up observations, allowed James Webb to not only identify enormous numbers of candidate ultra-distant galaxies, but to confirm their distances and identify features within them. Prior to the historical launch of James Webb, the most distant galaxy in the known universe was GN-Z11, which was observed by the Hubble Space Telescope and which set the cosmic distance record back in 2016. When James Webb began science operations in 2022, it was still the most distant confirmed galaxy known to humanity. However, as of late 2024, not only is GN-Z11 no longer the record holder, but it isn't even in the top 10. All 10 of the most distant galaxies were discovered or had key features detected by James Webb that confirmed their great distance, with the JD's collaboration spotting and confirming the current cosmic record holder, JD's GS-Z18-0. This ultra-distant galaxy is truly remarkable in a number of ways. Its light comes to us from just 285 million years after the Big Bang, when the universe was 2.1% of its current age. It overlaps with a brighter foreground galaxy, but thanks to James Webb's incredible resolution, we can disentangle the two galaxies, revealing the more distant background object in detail. It has a redshift of 1432, meaning that the light we're observing has been stretched by an additional 1432% of its originally emitted wavelength by the time James Webb observes it. However, there are arguably two properties of this galaxy that came as a glorious set of surprises. First off, this galaxy was bright. Not only brighter than our leading theories would predict, but substantially brighter than even previously observed ultra-distant Webb galaxies. And second off, there's extremely little dust in this galaxy. Again, something that defies predictions. Scientists called such impossible early galaxies universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, the current story of the universe doesn't predict nearly enough dark matter halos in the early universe as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model, and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. Elsewhere, the Supreme Observatory has also broken many other cosmic distance records. It discovered the earliest proto-cluster of galaxies ever seen by finding 7 independent galaxies in the same narrowly confined region of the sky that are all at the precise same redshift, 7.88, corresponding to an epoch just 650 million years after the Big Bang. This proto-cluster of galaxies, known as A2744ZMP90D, broke the old record by an impressive 150 million years. Moreover, instead of just appearing as single, red dots that were indistinguishable from individual point-like sources, many of these early galaxies appear to be extended objects, and some may even exhibit signatures of having satellite companions, rich details that would have been impossible to observe without Webb's capabilities. Hundreds of ultra-distant galaxy candidates, including dozens that may yet break James Webb's newly set records, have also been found in this early Webb data. The most distant gravitational lens ever discovered was found with the telescope by pure serendipity in a 2023 study. Many of the most distant supermassive black holes of all time, including the 4 most distant of all, have been found thanks to James Webb as well, including a remarkable one in the galaxy UHZ1, where the Webb Telescope in infrared light and Chandra in X-ray light teamed up to find a supermassive black hole of approximately double the mass of the one at the Milky Way's center, but where only about 10 million solar masses worth of stars are found in that galaxy. Although it's no surprise that James Webb could reveal these objects, the mass ratios between the black hole and the total number of stars in galaxies such as this were wildly unexpected. Moreover, the Webb telescope also conducted what many would call mundane observations, following up on objects that have captivated astronomers for generations and that have been observed hundreds of times before. For example, James Webb took a deep look at the Crab Nebula, a supernova remnant that was born with the core collapse of a massive star nearly 1,000 years ago, back in 1054. In the 970 years since, the Crab Nebula has expanded and grown to be some 11 light-years across, showcasing the power of a supernova explosion even a millennium later. With its sensitivity to features very difficult to resolve with prior observatories, it may yet resolve the mass mystery. Why the central pulsar plus the material in the supernova ejecta doesn't add up to the minimum mass of 8 solar masses thought necessary to trigger a core collapse supernova. It peered inside the Orion Nebula, which is the closest large star-forming region to Earth. Inside, it sought to better image protostars, along with mapping out the neutral matter and dust inside of it. Sure, it succeeded in those endeavors, but it also found something that was wholly unexpected with its infrared sensitive capabilities. An enormous number of Jupiter mass and super Jupiter mass planets that were freely floating inside these star-forming regions, planets without parent stars of any type. Not only was the discovery of these planets a surprise, but a whopping 9% of them were found being bound together in binary pairs, making them Jupiter mass binary objects, jumbios, a class of object not even known to exist prior to James Webb. When the telescope peered inside the well-studied El Gordo galaxy cluster, it found some spectacularly shaped gravitational lenses, which is precisely what you'd expect to find in a large, massive, but distant galaxy cluster whose gravity can curve and distort the space-time it occupies. As a result, background objects are lensed, distorted, stretched, and magnified, often appearing as multiple images at once. Also found in that field, however, was something never seen before: a single red supergiant star located at cosmological distances, only visible to James Webb because of the combination of its capabilities, along with the lensing properties of the El Gordo galaxy cluster. Known as Quiller, the Quechua term for star, it's located more than 10 billion light-years away. Meanwhile, the Webb telescope also observed a large number of relatively nearby galaxies that had three important properties. First, they were rich in Cepheid variable stars, which is a special type of star that varies in brightness over time with a well-known relationship. Second, they were found in galaxies that also housed, at one point, at least one type Ia supernova, making them important connecting rungs in the cosmic distance ladder method of measuring the expansion rate of the universe. And last, they were far enough away that pre-existing observatories, such as Hubble, couldn't resolve Cepheids very well on an individual basis in these crowded star fields. Was this field crowding issue biasing our cosmic distance ladder? James Webb was capable of asking and answering that question, and the answer is a resounding no, demonstrating that the Hubble tension and the mystery over the expanding universe is just as strong as ever, all while greatly reducing any possible sources of error. However, perhaps the single most surprising discovery made by James Webb came from looking at the bright nearby star Fomalhaut, one of the top 20 brightest stars in the night sky and one that's located only 25 light-years away. It's also a very young stellar system, so young that it still has a dust-rich debris disk surrounding it, something that hasn't been true of our own solar system in nearly 4 billion years. There were hints that there might be an exoplanet in this system, and the Webb time was allocated to a team that wanted to search for it. With its high-resolution capabilities and sensitivity to long-wavelength infrared light, there was a chance that James Webb could have directly imaged such a world. However, the story that the observations wound up telling was a completely unexpected one. Seeking a potential planet, James Webb instead found an inner disk, corresponding to the inner planets, and an asteroid-like belt, an outer ring, previously seen by Hubble and ALMA, corresponding to a Kuiper-like belt, an inner gap, and an outer gap in these features, corresponding to the location of likely exoplanets, and the real shocker, an intermediate belt, something with no analog in our own solar system. This shocking and surprising discovery is now leading us to ask a question we didn't even know we needed to ask. How many belts does a typical stellar system actually have? Is 2 the number that we possess, common or uncommon, or even a cosmic rarity? From a cosmic perspective, James Webb has shown us many things we could have expected, but has delivered a tremendous number of surprises as well. It's broken the cosmic distance records in many regards. For most distant galaxy cluster, most distant red supergiant, most distant gravitational lens, and most distant supermassive black hole, among several others. But what it's taught us about the universe, and in particular, about how our cosmos grew up, have included surprises that no one could have anticipated prior to James Webb unleashing the power of its discovery potential onto humanity. Do stellar systems like our own solar system have 2 belts, 3 belts, or some other number of belts in general? And which configuration is most common? We didn't know to ask this question before Webb era. What types of non-stellar systems are birthed when stars form, and are super-Jupiter planets and systems with Jupiter mass binary objects in them just the tip of the iceberg? We didn't know that jumbos existed prior to James Webb. How do supermassive black holes truly form in the universe? And do these Webb's findings rule out the possibility that they arose from the first generations of stars? The answer seems to be yes, incredibly. Now that field crowding of Cepheids has been ruled out as the cause of the Hubble tension, what is its ultimate resolution? Still an open question, but one potential contaminant has been eliminated. And despite their initially surprising abundances and brightnesses, are the earliest galaxies seen by James Webb truly consistent with our consensus picture of the universe? The answer again appears to be yes, as those properties of galaxies are mostly attributable to bursty star formation and the enhancement of light from supermassive black hole activity. Put simply, the Webb Telescope has taught us an incredible amount of information about the universe already, including what it's like, how it grew up, and how it created stellar and planetary systems, both different to as well as similar to our own. With another 20 years of science operations to look forward to, the only thing we can be certain of is that the records James Webb has set, as well as the science questions it's raised and begun to answer, are a harbinger of a great many discoveries still to come. In the meantime, let's take a quick look at a recent remarkable made by James Webb. According to its latest data, the telescope compels us to ask, what's wrong with Vega? The fifth brightest star in our night sky is young, blue, and apparently devoid of massive planets. And new observations made by James Webb has just deepened the mystery. Vega and Fomalhaut, one of the brightest stars captured by James Webb, are very similar in a lot of ways. Vega is the brightest star in its constellation, Lyra, and is actually the fifth brightest star in the entire night sky, surpassed only by Sirius, Canopus, Alpha Centauri, and Arcturus. Vega is also about double the mass of the Sun, 2.15 solar masses, as opposed to Fomalhaut's 1.92 solar masses, and is a little more luminous, larger in physical size, and hotter than Fomalhaut as a result. It's also 25 light-years away, and also like Fomalhaut, has a slightly smaller amount of heavy elements within it than the Sun does. Vega is also a little bit older, with an estimated age of 700 million years, but it still appears to have a debris disk around it. This happens to correspond to approximately the same time in our solar system's history when we think our debris disk disappeared, and the period of heavy bombardment of solar system bodies ceased. Remarkably, a team-up happened in the early 21st century between NASA's Spitzer Space Telescope in the mid-infrared and ESA's Herschel Space Observatory in the far infrared to show that there are likely two prominent features around Vega: a cool outer belt, which appears to be an analog of our Kuiper belt, and a warm inner belt, which could correspond to an analog of our asteroid belt. However, it would take future observations and a superior set of knowledge to be certain. Now, it's not exactly a shock that there would be new features revealed by new generations of observatories. After all, that's often the whole point behind why we build them: to find, identify, and characterize features that go beyond the instrument limits of all prior observatories. It's why it's so important that we observe the closest examples of classes of objects in order to better measure their properties, and it's why we have to hold on to a wide variety of examples of objects, including the unusual outliers that we see if we want to obtain a comprehensive understanding of such systems. For example, we've looked at GW Orionis and found evidence for planets, as well as disconnected ringed debris features that orbit around all three stellar members within this system. We've looked at large numbers of planetary systems still in various stages of formation with ALMA and discovered just how ubiquitous these features are: disks with gaps in them indicating planets, as well as large amounts of mass still present in the dusty portions of the disk, often hundreds of times the mass of planet Earth. What we've found is that planet formation and the presence of features in such disks appears to be inevitable so long as enough time has passed since nuclear fusion first ignited in that star and so long as there is a sufficient abundance of heavy elements within the star in question. But you might wonder if this general picture truly applies everywhere, or whether there are exceptional systems out there that defy this inferred trend. Perhaps you might wonder whether the other Fomalhaut-like systems are all either like Fomalhaut, with 3 belts and many gaps, or like our own solar system, with 2 belts and 8 major planets, or whether there are other examples for even the general configurations that stellar systems and their planets can take on. Are there 1-belt or no-belt systems out there? Are there 4-belt or more systems that abound? Are there heavy element-rich systems that don't appear to have any planets at all around them? As is often the case, these questions are indicative of questions we should always be asking, even when we don't have the necessary resources at our disposal to answer them. We should keep our minds open to a wide variety of possibilities, even when the data only indicates a small number of examples, with a small number of represented solutions. We should remember to refrain from making assumptions about what should be there before we have a sufficient amount of data to show us what actually is there. Of course, we don't always successfully do this. The temptation to draw sweeping conclusions from the data we have is difficult to resist. But with Vega, we have a new example of a debris disk system, and with new Hubble observations as well as the first James Webb observations, we now have something fascinating to consider. First off, the Hubble observations represent the deepest search we've ever done for scattered light around the Vega system. Because Vega is hot, close, and has a large debris disk around it, out to more than 170 astronomical units, or 4 times the distance to our Kuiper belt, and because the Hubble Space Telescope, like James Webb, is equipped with a coronagraph, we can perform a set of steps where we model the light from the star itself, model a dusty disk of debris with the appropriate thermal gradient, and then look for features or imperfections within that disk by subtracting the simple model from the actual data. The team working on this was able to achieve the lowest surface brightness sensitivities to date, as little as 0.004 MJY arcsec2, and they do in fact detect evidence for a scattered light dust halo. If the halo is composed of small dust grains and extends from where the Hubble data indicates, from 80 to 230 astronomical units, then there's no clear distinction between the parent planetesimal belt, previously observed by ALMA, and the extended dust halo. This means that, despite the similarities between Fomalhaut and Vega in age, distance, brightness, and heavy element abundance, their disks and the suspected presence of planets inside are vastly different. This set of differences only intensifies when we then add in the newest data obtained by James Webb. Using multiple different photometric filters with the MIRI camera, the astronomers who measured this system with James Webb were able to directly image the dusty debris around Vega, and what it found was as remarkable as it is surprising. First off, there is a planetary debris disk around Vega, and unlike the disk around Fomalhaut, it is smooth, symmetric, and centered on the star to great accuracy. This indicates that the disk is practically oriented face-on to us. Second, coincident with the ALMA data that revealed a planetesimal belt, is a broad Kuiper-like ring that extends from 80 astronomical units away from Vega all the way to 170 astronomical units, one of the largest Kuiper-like belts ever seen. Third, interior to that belt is more smooth, symmetric debris with only a very slight dip at about 60 astronomical units away from Vega, potentially indicating a small, low-mass planet that must be much less massive than Saturn, and that could realistically be no more massive than about 6 Earth masses. This is only about 30% the mass of Uranus or Neptune. And finally, there is a boundary or edge to the inner disk of the Vega system that terminates about 3 to 5 astronomical units away from the star, consistent with where our own asteroid belt is located. The big question then becomes how to interpret this data, or how to translate from these observations into what it means for the Vega system as a whole. As far as planets go, the only evidence we have is for one planet, much less massive than Saturn, and probably no more massive than a mini Neptune-type world, located at a large, just 60 astronomical units from the star, or about double the Sun-Neptune distance. And for a planet potentially as massive as Neptune in the inner 3-5 astronomical units of this system, separating the inner edge of the warm debris from the hot zone closest to the star. For the remainder of the system, from about 5 to close to 60 astronomical units, and thereafter from 80 astronomical units on out, there is no evidence for any other planets anywhere in this system. By combining data from Hubble, ALMA, and James Webb, scientists can infer that the halo of dust grains in the Vega system that's interior to the broad outer belt are of a small but not submicron size, likely being dragged inward by the pressure exerted by solar radiation on dust grains of that particular size. Astronomers call this the Poynting-Robertson effect. The part that's most surprising? That we have a massive star, more than twice the brightness and size of our Sun, with a surface temperature of around 10,000 K and about 47 times as intrinsically bright as our Sun is. That's already 700 million years old, and yet with no evidence for giant planets around it at all. Furthermore, there's strong evidence against any Saturn mass or greater planets within the Vega system at all. If you were playing exoplanet bingo, it's very unlikely this one would have even been an option on any one player's card. So what's going on? Where are all of the planets that one would have expected around a young, bright, massive star that already went through its planetary formation phase? Why is this disk so smooth and uniform, with so little hints of differentiation, save for one tiny dip at double the Sun-Neptune distance and one inner gap that could reveal up to a Neptune-mass planet at around the distance of either our asteroid belt or up to the distance of Jupiter? The short answer is, this is the power that you only get by taking a transformational leap in your observing capabilities. When you upgrade from an instrument like Spitzer, with less than 10% of James Webb resolution and under 1% of its light-gathering power, to one like James Webb, the novel technical capabilities bring along with it an enormous amount of discovery potential, the ability to discover new objects, phenomena, or features that would have otherwise been invisible to all past observatories. The reason you build telescopes like James Webb isn't because of what you know you'll be able to find, but rather because of what types of measurements you know you'll be capable of, and because of what those measurements might enable you to uncover about nature itself. Just weeks ago, we didn't know what to make of Vega or what questions to be asking. Now it's clear we need to be asking, why and how are there no large planets plowing through this debris disk? Planet formation is expected to begin no later than 2 million years into a star's lifetime, and is expected to largely complete by usual 10 million years into a star's life. But here we are, some of the 700 million years after the formation of Vega, and there's scant evidence of any planetary structure at all. Why? How? Is this common or rare? And what is the full variety of the types of planetary systems that are out there? In James Webb era, we're finally learning what the right questions are to be asking. The answers, whatever they may be, will have to await future observations before we can uncover them. The James Webb Telescope is a giant leap in the history of stargazing. With its advanced capabilities, including its ability to peer back in time to the very first galaxies that formed after the Big Bang, the Supreme Observatory is expected to shed light on fundamental questions about the origins and evolution of the cosmos. However, more than 2 years after operation, the telescope, albeit solved a lot of puzzles, is raising big questions about the early universe. The data obtained by James Webb isn't just quite what scientists expected. So, though dazzled by Webb's stunning images of deep space, scientists had to admit that something was amiss. What the telescope has revealed contradicts scientists' current theory of how the universe grew up, and it's beginning to look as if we may need to rewrite the history of the cosmos and reshape humanity's position within it. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. The James Webb Space Telescope, as you know, is one of the most advanced telescopes ever built. Planning for James Webb began over 25 years ago, and construction efforts spanned over a decade. It was launched into space on December 25, 2021, and within a month arrived at its final destination, 930,000 miles away from Earth. Its location in space allows it a relatively unobstructed view of the universe. The telescope design was a global effort led by NASA and intended to push the boundaries of astronomical observation with revolutionary engineering. Its mirror is massive, about 6.5 meters in diameter. That's nearly 3 times the size of the Hubble Space Telescope, which launched in 1990 and is still working today. It's a telescope's mirror that allows it to collect light. Webb's is so big that it can see the faintest and farthest galaxies and stars in the universe. Its state-of-the-art instruments can reveal information about the composition, temperature, and motion of these distant cosmic objects. Thus, for thousands of space scientists, the James Webb Space Telescope is a window to that unknown universe. Just how far back can James Webb peer into the cosmos and into the past? Well, about 13.5 billion years. A telescope does not show stars, galaxies, and exoplanets as they are right now. Instead, astronomers are catching a glimpse of how they were in the past. It takes time for light to travel across space and reach our telescopes. In essence, that means a look into space is also a trip back in time. This is even true for objects that are quite close to us. The light you see from the sun left it about 8 minutes, 20 seconds earlier. That's how long it takes for the sun's light to travel to Earth. You can easily do the math on this. All light, whether sunlight, a flashlight, or a light bulb in your house, travels at almost 300,000 kilometers per second. That's just over 18 million kilometers per minute. The sun is about 150 million kilometers from Earth. That comes out to about 8 minutes, 20 seconds. But the farther away something is, the longer its light takes to reach us. That's why the light we see from Proxima Centauri, the closest star to us aside from our sun, is 4 years old. That is, it's approximately 40 trillion kilometers away from Earth, so that light takes just over 4 years to reach us. Or, as scientists like to say, 4 light years. Most recently, James Webb observed Earendel, one of the farthest stars ever detected. The light that the telescope sees from Earendel is about 12.9 billion years old. The Webb Space Telescope is looking much farther back in time than previously possible with other telescopes, such as the Hubble Space Telescope. For example, although Hubble can see objects 60,000 times fainter than the human eye is able, the Supreme Observatory can see objects almost 9 times fainter than even Hubble can. But is it possible to see back to the beginning of time? The Big Bang is a term used to define the beginning of our universe as we know it. Scientists believe it occurred about 13.8 billion years ago. It is the most widely accepted theory among physicists to explain the history of our universe. The name is a bit misleading, however, because it suggests that some sort of explosion, like fireworks, created the universe. The Big Bang more closely represents the appearance of rapidly expanding space everywhere in the universe. The environment immediately after the Big Bang was similar to a cosmic fog that covered the universe, making it hard for light to travel beyond it. Eventually, galaxies, stars, and planets started to grow. That's why this era in the universe is called the Cosmic Dark Ages. As the universe continued to expand, the cosmic fog began to rise, and light was eventually able to travel freely through space. In fact, a few satellites have observed the light left by the Big Bang, about 380,000 years after it occurred. These telescopes were built to detect the splotchy leftover glow from the Big Bang, whose light can be tracked in the microwave band. However, even 380,000 years after the Big Bang, there were no stars and galaxies. The universe was still a very dark place. The cosmic dark ages wouldn't end until a few hundred million years later, when the first stars and galaxies began to form. The James Webb Space Telescope was not designed to observe as far back as the Big Bang, but instead to see the period when the first objects in the universe began to form and emit light. Before this time period, there is little light for the James Webb Space Telescope to observe, given the conditions of the early universe and the lack of galaxies and stars. Peering back to the time period close to the Big Bang is not simply a matter of having a larger mirror. Astronomers have already done it using other satellites that observe microwave emission from very soon after the Big Bang. So the James Webb Space Telescope observing the universe a few 100 million years after the Big Bang isn't a limitation of the telescope. Rather, that's actually the telescope's mission. It's a reflection of where in the universe we expect the first light from stars and galaxies to emerge. By studying ancient galaxies, scientists hope to understand the unique conditions of the early universe and gain insight into the processes that helped them flourish. That includes the evolution of supermassive black holes, the life cycle of stars, and what exoplanets, worlds beyond our solar system, are made of. However, data obtained by James Webb isn't quite what scientists expected. In the 2024 Isaac Asimov Memorial Debate, astrophysicist and science communicator Neil deGrasse Tyson moderated a discussion at the American Museum of Natural History in New York. The conversation was between scientists and surrounded the topic of how data from the telescope may be shifting our fundamental understanding of our universe. From discrepancies in the age of the universe to the unexpected brightness of early galaxies, the James Webb Space Telescope has already prompted scientists to reconsider how the early universe once operated, leading to revelations that could trigger major shifts in our models of the universe during the next decade or more of James Webb's tenure. And in the words of panelist Mike Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, the data from the telescope paints a consistent and consistently new picture of the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies. Far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe. And they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, the current story of the universe doesn't predict nearly enough dark matter, halos in the early universe as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget, there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. What's notable, the impossible early galaxies aren't even the only things that keep cosmologists up at night. The Webb Telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary, the trailblazing observatory found, further ratcheting up the so-called Hubble tension. Putting it simply, measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone such as Cepheid variable stars and Type 1 supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is, this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. The 5 galaxies observed by James Webb, the most distant of which is NGC 5468, at 130 million light-years from us, have also hosted a combined total of 8 Type Ia supernovas over recent decades. These supernovas which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, Webb's observations of Cepheid variables therefore makes the distance measurements using Type 1 a supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. In the words of Rees, we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains is the real and exciting possibility we have misunderstood the universe. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. In other words, the tension at the heart of cosmology is here to stay. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. After all, there is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets, and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It is up to us to coax those secrets from its grip, transforming them from mystery into discovery. In a recent remarkable finding, James Webb has discovered that early universe galaxies must have grown up way faster than expected. Plus, the same team also found that 10 billion years ago, the cosmos wasn't quite as disordered and chaotic as previously believed. The international team, led by researchers from Durham University in the UK, reached these conclusions by discovering evidence of structures called star bars, forming in galaxies that existed just a few billion years after the Big Bang. Star bars are elongated regions of increased star density found at the hearts of spiral galaxies like the Milky Way and other disk galaxies. As they form, star bars push gas toward the hearts of their respective galaxies, thereby regulating starbirth. The presence of these central bar structures thus indicate that a galaxy has entered a more settled and mature phase. As Zoe LeConte, team leader and a researcher at Durham University, said in a statement, "Galaxies in the early universe are maturing much faster than we thought. This is a real surprise because you would expect the universe at that stage to be very turbulent, with lots of collisions between galaxies and a lot of gas that hasn't yet transformed into stars. However, thanks to the James Webb Space Telescope, we are seeing a lot of these bars much earlier in the life of the universe, which means that galaxies were at a more settled stage in their evolution than previously thought. This means we will have to adjust our views on early galaxy evolution. Notably, this isn't the first time scientists have gone bar hopping in the early history of the 13.8 billion year history of the universe. The Hubble Space Telescope witnessed these features as well, but that orbiting eye on the universe could only go as far back as 8 billion to 9 billion years. However, the increased sensitivity and wavelength range of James Webb has stretched such observations back at least another 1 billion years. This has revealed bar formation in galaxies that are seen as they were between 8 billion and 11.5 billion years ago. In fact, of 368 disk galaxies the team considered for the study, 20% already had bars. That is double the number observed by Hubble. The further back in time the team looked with James Webb, the fewer bar structures they observed in galaxies. They believe this could be because galaxies at earlier stages of the universe were not as well formed. An alternative may be that shorter bars were more common in progressively earlier galaxies. Even the impressive observational power of James Webb isn't sufficient to see these short bars in early galaxies. With these results in hand, the team now wants to use the telescope to peer even further back into cosmic time, looking back as far as 12.2 billion years ago. This could reveal whether bar growth was common just 1.6 billion years after the Big Bang. As Gadati concluded, the simulations of the universe now need to be scrutinized to see if we get the same results as the observations we've made with the James Webb Space Telescope. We have to think outside of what we thought we knew. In another observation, the Webb Telescope has discovered the oldest dead galaxy ever seen. But the cosmic corpse has left scientists puzzled as it defies explanation by our current knowledge of the early cosmos. The galaxy suddenly and mysteriously halted star formation when the universe was just 700 million years old, when countless stars were birthing thanks to an abundance of pristine gas and dust elsewhere in the universe. The galaxy, named Jade's GS Z701QU, and described in a paper published in the journal Nature, provides astronomers with a peek into the elusive underpinnings of galaxy evolution in a primordial universe, including why galaxies stop forming new stars and whether forces driving their starbursts alter across epochs. In the words of study lead author Tobias Lusser, a researcher at the University of Cambridge's Kavli Institute for Cosmology, Cambridge or KICC, galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. Current models cannot explain how the newfound galaxy not only took shape in less than 1 billion years after the Big Bang, but also shut down its star factory so quickly. According to study co-author Francesco Diogenio, also a researcher at KICC, it's only later in the universe that we usually start to see galaxies stop forming stars. In comparison, a handful of other dead galaxies found elsewhere appear to have paused forming new stars when the universe was about 3 billion years old. To discover Jade's GS Z701QU, Lusser and his colleagues used James Webb's powerful infrared vision to peer through the thick veil of dust obscuring the earliest objects in the universe. In addition to being the oldest dead or quenched galaxy spotted so far, the newfound galaxy is also many times lighter than other similarly quiescent galaxies previously found in the early universe. Webb's data suggest the galaxy intensely formed stars for somewhere between 30 million to 90 million years before it rapidly shut off, although precisely what ended it is still unknown. Astronomers know of a couple different factors that can slow down or extinguish star formation. For instance, turbulence inside a galaxy, such as radiation emitted by a supermassive black hole, can push gas out of the galaxy and starve it of the gas reservoir it relies on to form stars. Another intriguing possibility is that the galaxy's surroundings at the time did not sufficiently replenish the gas reservoir being consumed by birthing stars, leading to a deficit in star-forming material. However, in the words of study co-author Roberto Maiolino, an astrophysicist at KICC, we're not sure if any of those scenarios can explain what we've now seen with Webb. Current models based on the modern universe are unable to explain the properties of Jade's GS Z701QU, suggesting they may need to be revisited. Another possible explanation for the new galaxy's dormancy could be that galaxies in the early universe die and then burst back to life. However, previous research of dead galaxies from when the universe was around 3 billion years old, a time of its most prolific star birth, suggested such dead galaxies cannot rejuvenate even via mergers with nearby galaxies, which instead only serve to puff them up. As Eugenio said, we'll need more observations to help us figure that out. A quick note, James Webb now is digging deep into the mysteries of gas planets. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The short answer is not very long, but the full story is far more nuanced. The research team used the Webb Telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. According to Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, we knew that they exist and that they might play an important role in disk evolution. What we didn't know was the underlying physics, and consequently, how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. According to Bajaj, considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about one moon mass every year, it will take approximately 100,000 years. Yes, that sounds like a long time. But, as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. After all, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, James Webb should look. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.